Hey everyone, Sebastian here, and I wanted to make a video talking about performance in the blockchain setting, which is of course a popular topic. Notably, I want to focus on confirmation time, sometimes otherwise called as finality. And this is an important topic because it allows you to make systems that are more reliable. It allows you to give a better user experience, allows developers to have a better time building systems on top of the core blockchain. So what does that actually mean? What is, finality? Well, when people talk about performance of a blockchain, they often talk about three different things. One is throughput, right, which is how much data can you actually push through the blockchain. And so the higher the throughput, the higher your max transactions per second. So this is obviously a topic that's the most looked into, but there's a few other things you might want to think of. For example, you could think about latency between nodes in the system. How long does it take for a transaction to propagate across the network to all the nodes? But there's another topic that we're going to be talking about primarily today, which is finality, which is once a transaction is propagated to the system, all the nodes are aware of the transaction and it gets included in a block, right? So this gets included in a block. How long until we know that this block will stick around? It will not be deleted. It will not disappear. This transaction will really stick around. And that might seem like a bit of a strange question, right? If you're not familiar with the blockchain space, why would a block ever disappear? Why would a transaction ever make it into a block and then not stay there forever? And to answer this question, you have to think about a decentralized system, right? So imagine you have a world where you have, Asia on one side and North America on the other. And, maybe I'm over here and I send a transaction to somebody over here. They include that into a block in the network, so they're like a stake pool operator or a block producer. And then the person who makes that block then sends it out to other nodes in North America. And of course, because of the speed of light and other similar factors, that transaction will first reach all the other nodes in North America and then eventually make its way across Asia. So note that there's kind of a latency between me making the transaction here and then going to the nodes, including the block, going to different things, eventually making the hop over. So there's a certain time that it takes to do this. But what if I, for example, send the same transaction directly to Asia in the meantime? Right, so I send it to this node over here, and in parallel to this, I also send it to Asia. And some node in Asia sees this, and maybe they make a block that includes that transaction. And then they, of course, send it to other nodes in Asia. One of them which might become, block producer or propagator, and they send that node over here. But now we have a conflict, right? There's the transaction that got included in this block here, and I sent the very same transaction that got included in a different block here. And it took a bit of time for the parties to communicate over the Pacific Ocean and realize, like, wait a minute, we have two different blocks by different people that include the same transaction. And obviously, if the details don't match, then this is an issue, right? We can't have this person spending the same tokens in two different places. That would break the network and allow you to, double spend, so to speak. So in this situation, what often happens is what's called a rollback, which is like, okay, we thought we had a right block here. We propagated, we thought, okay, this is it. The users made a transaction, and then we actually realized, like, actually, wait a minute, the user made a different transaction in a different geography, and that got included in a block, and maybe that one made it to Europe already, and so Europe already knows about this block, and well, actually, there's more people that think this is the real state of the network than people think it or is the state of the network in North America. So actually, like, we're wrong. We thought this was how the user is going to spend their money, but they send it to somebody else instead, and that's already propagated through the rest of the world. Therefore, we're gonna roll back. So we're gonna say, okay, you guys are right, we're wrong. We're not gonna we're not gonna try and convince you guys that this state of the network is real. We're instead gonna say, okay, well, assume the yellow was the real state, and we're just going to adopt it. So that means that the nodes in North America performed what is called a rollback. They thought they had the right state of the system, but they undid that state and apply the states they got from a different area, right? So because of these rollbacks, the possibility of these rollbacks, when you see a transaction in a network, there's no guarantee that it is correct right away. You have to wait a bit of time. And this matters because if you look, for example, at Bitcoin, the blocks are around 10 minutes. So you have to wait 10 minutes for the first inclusion. But then the finality is often said to be around 60 minutes, which means that you have to wait a bit of time to give enough time for the nodes to propagate transactions across the entire world and come to a consensus about the current state of the ledger. So this is approximately 60 minutes, and approximately 10 minutes. These are like averages. And you might think, well, okay, well, Bitcoin's, an old technology that doesn't really affect new networks, but actually it does. So for example, in Ethereum, blocks are about 12 seconds approximately. But oftentimes people like to wait between 10 to 15 minutes for finality. You could say this is a bit overkill. Usually you don't have to wait this long. But this is especially notable on things like exchanges, where, for example, the exchange wants to be really, really sure that the ETH that they're sending out is not going to get rolled back. So exchanges usually take a bit longer to process withdrawals. And so you can also see this on networks like Cardano, which has 20-second block times approximately. And then finality, usually you can get away with waiting things like approximately 2 minutes is usually like when you're safe. But if you want to be really safe, you'd have to wait 1 day. And so if you want to be like 100% sure, I would recommend waiting a day. But of course, this is introducing a bunch of issues, not just for exchanges, right? So it affects exchanges who have to process withdrawals, but it also affects other systems. So for example, like layer 2s, right? So remember, Ethereum is a layer 1 blockchain, but there are multiple layer 2s that are connected to it. And these layer 2s want to know when their data has been included inside Ethereum, right? So different layer 2s are submitting data to Ethereum, and they want to know, well, when is the data submitted to Ethereum finalized? And if they want to wait until full finality, they actually have to wait for this. And so this can be annoying when you want to make, transfers between layer 1 and layer 2. If you want to give the user full finality and tell them, like, okay, like, at this point, you're 100% sure it's not going to be rolled back, it introduces kind of a delay. So this is a problem. But it's a problem that, another thing is it also affects, sorry, I forgot to mention, transaction chaining. So maybe you want to have multiple transactions that depend on each other. So you have transaction 1 you want to submit, and once that makes into a block, you have transaction 2 you want to submit, and then once that's included in the block, you want to make it transaction 3. So it also affects the performance of transaction chaining. So note that this affects multiple networks, like I mentioned, but it does not affect every network. Notably, the commonality between these 3 networks I mentioned is that they use a type of consensus called Nakamoto consensus, which is a very popular consensus implementation for decentralized blockchains because it has a really good ability to recover in the case of adversary attacks. It has oftentimes 50% resistant to adversaries, so an adversary would need to control more than 50% of the network to attack, and tends to just overall be more resilient, which is a property that a lot of blockchains want. However, there are some blockchains that prefer to not deal with this slow finality and instead focus on trying to have faster finality. So in that family of blockchains, you have stuff like Solana, Algorand, Sui, Aptos, and so on. So these blockchains operate at a much faster finality. So oftentimes you get finality either in a few seconds, or sometimes in the case like Algorand, you have finality instantly. As soon as the block gets made, you get finality right away. Now, this comes with some trade-offs in decentralization, but also in some other factors that make these networks a bit less reliable in theory. And the proponents of these kinds of systems will often say, well, in theory, maybe that's the case. But in practice, for example, like the Algorand blockchain has never gone down. So you can say, like, okay, well, maybe theoretically there's some benefits in Nakamoto consensus, but if we've been operating a network for many years and we've never run into an issue, but we've been able to get fast filing for all users, like maybe this is worth it as a trade-off, right? And these kinds of networks often are called like BFT-based consensus. Notably, if you want to know the difference between Algorand and Cardano specifically, because out of all these networks I mentioned, these two are actually kind of similar in a lot of ideas. So they're both proof-of-stake systems. They both depend on VRFs and elections. And actually, I have a video that compares these two blockchains exactly and how the consensus differs. So I'll have a link below if you want to know what is the difference between this BFT-based system, this Nakamoto-based system, and the actual concrete implementation of how it selects block pools, block producers, and all this kind of stuff. I have a video exactly on that topic. But we're going to talk a bit about that very briefly in later on this video. So if you don't want to go watch another video, we'll cover some stuff. One thing you might be wondering when you hear me talk about this is, can we have both, right? Can we have the benefits of Nakamoto consensus, which is this really great resilience, while also having this BFT-based approach where you have very fast finality? And the answer is kind of. So the default answer would be no, and there's many topics you can look into if you want to learn more about them. So one of the popular things is CAP theorem. But essentially there's quite a few theorems similar to this theorem that essentially state impossibilities in decentralized systems. So it says okay, if you're building a decentralized system, you have to choose between a few different properties and you cannot have all of them. So for example, CAP theorem specifically is consistency, availability, and partition tolerance. So notably, the kind of way this relates to what we're talking about is that consistency means that you get the latest data always whenever you query a node, and availability means kind of hand waving, but the network is available for you to use. And so with a BFT system, a BFT-based protocol, because, for example, in Algorand you get instant finality, you get very good consistency. Whenever a transaction gets included and you query for it, you'll get the data. Because it's less resilient, you might run into an availability issue where the network, for example, in times of low participation, if there's not enough people online, the network might pause temporarily, waiting for more people to come online to keep creating blocks again. So there's not enough people to finalize the data that's around, and so it causes this kind of availability concern. So, these BFT-based and Nakamoto-based consensus, they have these trade-offs, and you have to pick between them. But you might remember I said kind of. What does that mean? You can actually have both of them in the same blockchain, which is, you could have a blockchain, for example, that would look, something like this, which is your regular chain of blocks. And you can say your blockchain to have two parts to it. You have the most recent blocks that depend on Nakamoto consensus. So, okay, the most recent data, you have this kind of very resilient system. That way, even if somebody tries to fork the network, and you have, for example, this is the US split and this is the Asia split. So even if you have this kind of split that happens, you still have a very resilient system. And then for historical data, for historical data, you have BFT. So at some point, there's some kind of transition point where nodes switch the kind of algorithm they use to give finality to the chain. And this is something that quite a few people have looked into. So, for example, Ethereum looked into this, and you can find some papers they were on the topic a few years ago, like, for example, Ebb and Flow. There's a paper there, some Ethereum people wrote quite a while ago, and they're basically talking about, like, the same thing, which is like the availability finality dilemma, which they called it, which is like, okay, we want to have fast finality, we also want to have availability as well, right? So they called this like the availability finality dilemma. But the problem with this kind of system is that it was very hard to prove correctness. In fact, you can find not only many papers of people attempting to build this idea, you can find probably an equivalent number of people who find flaws in these implementations. It turns out having two different consensus algorithms running at the same time for your network is very hard to wrangle and make work together. And the reason why it's hard to make these work together properly is because you want to basically fall back to Nakamoto consensus when something goes wrong in the network. So if things are looking bad, so there's potentially an attack going on or something's happening, you want to basically like ignore the BFT and have all the nodes automatically just rely on the Nakamoto consensus. And then eventually, once the attack is over, the network's looking better, things are looking healthy, you go back and re-enable the BFT. So you have this BFT protocol, but it's not a constant thing. Rather, it's the default, but occasionally you have periods where you have to disable it and rely solely on Nakamoto consensus until your network comes back to health. So you might hear this kind of term as like a cooldown or a cool off period or these kinds of things, which is like this time period where you have to disable the BFT and wait for the network to come back to health. And in fact, Cardano, for example, has done research on this that they call Ouroboros Peras, which is their way to take the Nakamoto consensus system they've implemented, but also have BFT for it. And they describe in their paper how to basically have the BFT system run in typical sense, but when a network is under attack, you disable the BFT part of the system. So before we get too much into that, let me just look at my notes real quick. Yeah, okay, so let's talk a bit about how Ouroboros Peras works, and how basically it helps implement the system. So typically, when you'd have a blockchain system, you might have, as we mentioned earlier, different forks that exist. And one of these might be like maybe nodes in US on some branch, and maybe nodes in Asia are in a different branch, and then maybe this is like US East and then US West is like on a different fork. So because it's a decentralized system, there's not really a good way to avoid the fact that people might get stuck on different branches in a Nakamoto consensus setting. So the question is, if somebody's coming into the network and they're synchronizing their node for the very first time ever, which state of the network is the real state of the network, right? Is this the branch of the network they should be syncing? Or should they be synchronizing this state of the network? Or maybe they should be synchronizing this state of the network, right? When you're a new person entering the system, you just started your node, which branch is real? And the way this is solved in proof of stake systems is you try and take the branch with the most stake weighting. So like maybe 30% of the network is on this branch, or 70% of the network is on this branch, and then here maybe okay, so if that's the case, then like this path is right. So you want to try and have an argument about like how much weight in stake is on which branch, and then that's more likely to be the real chain. This is actually hard to do in practice. So it sounds like it should be really easy, but in typical settings like in Cardano, you can't actually really know these weights that well. You have to approximate. And the reason why is because stake pools create blocks independently, right? So this is stake pool 1, This is stake pool 2. This is stake pool 3. This is stake pool maybe also 3. This is 4, 5. So note that every block is created by a different stake pool. And when a stake pool creates a block, they're kind of voting in a sense that like, oh yeah, I think this path is like the real state of the network. So by creating a block here, they're kind of voting on which path they think is the longest path. Because every block only contributes one stake pool, it can take quite a while for the state of the network to know which path is longest, right? So here, we had to wait, 4 additional blocks to get 4 different stake pools to vote on, which state of the network they think is the best one. And so because each block is only having one stake pool contribute to the finality, that's why it takes so long, right? And that's why you get these kinds of long delay periods, because you have to wait for multiple stake pools to make multiple blocks to see over time which branch has people voted on. So natural way you might want to solve this problem is to say, okay, well, the tip, the latest state of the blockchain, still is like before. You have, people voting just by making a block, and there's just one stake pool involved in that. But for historical blocks that have occurred enough in the past, we instead have other stake pools come in. And even though they didn't make this block, they're coming in and voting on it and saying, oh yeah, like this block that appeared in the past, I agree. Even though I'm not making a block, in this epoch, so I'm not, going to be voting by making a block, I still want to have my stake pool assert the fact that I think this state of the history is real, right? So we're moving to having stake pools votes only matter when they're creating blocks, to having stake pools votes matter basically for older blocks. For any older block, they're willing to come in and say, yes, I think it's the right state. Even though they didn't make block 1, they can come and say, yes, I think this is real. And so the core idea is if enough stake pools in the network come in and endorse a previous block, notably in Cardano, I think this is 75% that they're looking at. 75% of the active stake comes in and endorses a block. Then you consider this block as boosted. And this is like a term they use. So they consider this red thing as a boosted block. So note that they don't consider it finalized, rather they call it boosted. And the reason they do this is because they want to basically use this to help the weighting of the graph. Remember, we saw previously, like, one idea was like, you could say like, okay, this has 70% and this has 30%. And this has, 10%, and as somebody who's just coming to the network, you want to follow the path with the most weight on it. So this concept of boosted, know that you're essentially like, boosting these paths. You're taking the percentage and you're kind of increasing in a sense. So for example, if this becomes a boosted block, and you're a new person in the network and you're trying to figure out, okay, do I go on this chain or do I go on this chain? You say, okay, this one is a boosted block, which means there's a lot of different stake pools that have put their weight behind this one being the real state of the chain. So it's much more likely that this is the state of the network. So the concept of boosted block allows people to, sync the chain more reliably. And because they can sync the chain more reliably, it also improves finality, right? Because now, if we're considering a transaction that occurred in this block, it's more likely to become the real state of the network than a transaction that appears in this block. And if you have, even better, if you have a transaction that, occurs in this block, so here we have like a transaction in purple, we can, okay, well, the transaction that appeared inside this block has a very high chance of not being rolled back because, look, it's a boosted block that was boosted by so many stake pools that are active in the network. So great, now we have this way of creating boosted blocks that help us get faster finality, But how fast is the finality that we get? Well, in Ouroboros Peras, that's approximately 2 minutes. You might think, well, 2 minutes, that's still not super fast, right? So, for example, Algorand has block times, I think 3 seconds. I don't remember. I think maybe they moved it slightly under 3 seconds, but pretty fast, and they get instant finality, right? So why do we have to wait 2 minutes? And the reason why is because the faster you have the boosting, the faster the finality you get. So remember, we had this graph here where at some point we transitioned from the Nakamoto style system to the BFT consensus, right? So you can think of it as this is the point where we start boosting blocks. Everything like within the yellow square, these are blocks that pools will start to boost. But why do we draw the red line here, right? We could have built it here and tried to generate the boosted blocks faster instead of having this like a longer period where you have to wait until boosting. And the reason that we wait so long, we don't do it right away, is to avoid the cooldown period, right? So note that if we pick this point here as the part where we start boosting blocks and stake pools start boosting blocks, we get much faster finality. But if we have fast finality and something happens, for example, an adversary is attacking network, and we have to fall back, right? So we have to say, okay, the adversary is attacking the network, fall back, stop boosting blocks, fall back to Nakamoto consensus. Now we have a long period of no boosted blocks at all. So in good conditions, you know, if you have like the line for the boosted block here, in good conditions, it's super fast. Finality, which is great. You have super fast finality. But in bad conditions, as we mentioned, in bad conditions, we have no finality. Because remember, we said in a bad condition, we disable the BFT and fall back Nakamoto. So the question is, how often does this bad condition apply? How often does it happen? And it turns out that in Ouroboros Peras, the closer you put the transition point to the tip of the chain, the more likely this bad condition is to occur. So by having super fast finality, you're also increasing the likelihood that you have to fall back to having no finality for your period of time. And so based off of this, and in the documentation for Ouroboros Peras, you can find that they picked 2 minutes as what they felt was a good trade-off between having the barrier far enough that it still feels like it contributes to the fast finality of the network, but far enough to avoid the bad conditions ever really happening in practice, because ideally this never happens ever. You know, ideally this is not a thing that's like, oh, this happens every day. Ideally the bad condition happens never, right? And then now you get, you know, this faster finality for free. And so based off their analysis, they picked, you know, assuming an adversary has 25% adversarial stake in the network, by picking 2 minutes, they feel pretty confident that the bad case will never happen. But of course, these parameters will be up to DREPs and the governance of Cardano to choose. And so people might decide to say that 2 minutes is maybe playing it too safe, and they want to change the parameters and have faster finality and risk this bad condition. Or there might be more different improvements in the network later that allow you to make these changes. So this is kind of Ouroboros Peras in a nutshell. And I'll have a link below where you can find more information about Ouroboros Peras and how it works, both as a video form as well as the documentation. But you might be wondering, of course, well, can we do even better? Can we do even better than 2 minutes? So you might be tempted to think about other things you might have heard of, like Ouroboros, Laos, which is another thing that people have talked about a lot in the context of performance network. But Ouroboros Laos is a throughput improvement, right? It increases the TPS of the system. It is not a finality improvement, which is why I mentioned at the start of the video, where you have to keep in mind that finality and throughput are separate concepts, right? So Laos will not come solve the day. We have to think about different systems. Well, how are people doing this in other blockchains, right? Let's look elsewhere for inspiration. Well, there's, oops, let me unselect this. There's some ideas in Ethereum called preconfirmations. And this concept of preconfirmations is especially useful in the context of layer 2s. Right, so remember we said in a blockchain, you might have your layer 1 blockchain, but inside it you have many different layer 2s that are submitting data. So here I have layer 1 doing stuff, and then here we have a bunch of layer 2s that exist. Okay, and remember I mentioned that these layer 2s would like to have fast finality as well. And so how can they have faster finality? They can leverage this concept of preconfirmations. So what are these preconfirmations and how they work? Well, remember when we started graph earlier, we have each block created by a stake pool. So you'd remember this is stake pool 3, and this is stake pool 2, and this is stake pool 1, and this is stake pool 4. Where every block is created by a stake pool. And stake pools choose what to include in a block. Right? So if I know I'm going to make the block in the next 20 seconds, I can basically sell you the right to include something in my block. So I tell everybody, like, hey guys, I'm going to make a block in 20 seconds. Anybody want to include something in my block? Pay me money and I'll include whatever you want. And then these layer 2s say, like, oh yes, actually I would like you to include my transaction inside your block, and I'm willing to pay, you know, maybe like, you know, $10, for example, or like 10 ETH or 10 ADA or whatever you want. And so this is kind of an instance of MEV, which you might have heard of, which is minor extractable value, which is the block producers can earn more money the block rewards in networks. Remember, when you create a block on a blockchain, you usually get paid for it. So that's how block producers make money. They get paid for creating blocks. But MEV allows you to make even more money than what the protocol gives you by leveraging the fact you're making a block to do extra business. So in this case, I am selling the right to include a transaction in my block. And that's why it's called a pre-confirmation. Because you're essentially telling this layer 2, like, oh yeah, like I haven't made this block yet, but I will make this block. And once it gets made, you know, I will include your transaction, therefore pay me now. And so, of course, block producers could lie. And so usually there's some kind of concept of slashing conditions, which is that if the block producers lie, there's some kind of recourse where the person, for example, the layer 2 that paid can say, like, hey, this person said they would give me space in their block, and then they didn't. Here's the proof they said they would, and then I'll use this proof to slash them and maybe like earn $1,000 from their deposits by like slashing them. So it's like a punishment. If you lie, you get punished. And notably, note that these slashing conditions are not like a Discord conversation. It's not a Twitter conversation. This is like a protocol feature. So they have some system where if you can mathematically prove somebody lied to you, you can automatically, via a computer program, slash them and get $1,000. And notably, you might be wondering, like, well, that's a bit weird. Like, does that kind of system actually exist? And actually, it does. And not only does it exist, it's a very big system. It's a very popular concept. So, notably, you might have heard of systems like EigenLayer. which basically provide this kind of thing. Eigenlayer is basically like a slashing condition coordination, like or management. So anybody can create slashing conditions as long as it's provable by a computer program. You can register a slashing condition to Eigenlayer, and then you can use these slashing conditions you've registered to offer services. So for example, it's like, hey, I will sell space in my block for $10, and if I lie, you can use my slashing condition that I've registered on Eigenlayer to slash me for 1,000. So notably, this concept of these slashing conditions in Eigenlayer, more generally, it can be called an AVS, which is an actively validated service. Which is to say, the reason it's actively is because you have to actively monitor what the users are doing and then slash them if they do something wrong. Obviously, if nobody's monitoring the system, if somebody does something wrong, nobody's going to be around to slash it. So it requires you to actively monitor. Make sure that people are telling the truth. If they don't tell them the truth, somebody needs to go and slash them. And so that's why Eigenlayer is a kind of a large protocol, because a lot of people want to be able to register these kinds of slashing conditions. So you, just to maybe to go over some use cases that people have used Eigenlayer for, so you get maybe an idea. So of course, you could use this for layer 2s for pre-confirmation. It don't have to go through Eigenlayer, by the way. Like, this is a option, but like there's different ways to do this. I'm just using this as like one example. So you could have pre-confirmations through some kind of Eigenlayer system. You could have, for example, like watchtowers for state channels. So if you have systems like Hydra, for example, which is Hydra as the state channel, what if one of the state channels is being malicious? You could try and slash them through something like Eigenlayer. You have a lot of people using Eigenlayer to try and, just generally speaking, increase revenue for their block producers by opting to more services. So saying like, hey, my block producer does not just create Ethereum blocks, it also does this other service as well. And by offering this other service, I get more revenue. And this concept, of course, exists not just in Ethereum, but it exists in other blockchains as well. So for example, in Cardano, there's this concept of Mithril, which is a way for stake pools to opt into offering different services and being able to, with their stake, vote on, different things. And so you can think of Mithril as not exactly the same, but kind of similar to Eigenlayer. So the different systems, but a lot of the ideas are similar. And so Mithril is used for stuff like, the ideas of Mithril are used for stuff like Ouroboros Peras, which you saw earlier, which is like, these stake pools opt into an extra service. So instead of just creating blocks, I'm also now voting on the boosting of different blocks. You can think of partner chains, which is this Cardano concept of side chains, as being this extra service you validate. You can also think of like having stake pools offer Hydra heads as being this extra service. And note that these don't have to have slashing conditions. Like, Ouroboros Peras does not need to have a slashing condition. Partner chains don't need to have a slashing condition necessarily. So just because we're using some of these ideas does not mean like it works exactly the same way. It's more of a conceptual overhead, or not conceptual overlap, where for some of these services you might want to do something for the sake of the revenue, and just the revenue, or just providing the service. But in other cases, you might have some kind of system where you care about the slashing conditions. You might need to require a system that can handle slashing, with Mithril is by itself not handled to do. And you can see this in other blockchains as well. So for example, Algorand has state proofs. Which works conceptually similar to Mithril, more so than Eigenlayer. So just like Mithril, it doesn't have like this slashing condition, so it's less like Eigenlayer, it's more like Mithril. But you can see like a lot of different blockchains have come up with this concept, and notably, you can use this concept to implement preconfirmations. And because these preconfirmations are talking about the next block that's coming up right away, it can give you much faster finality. So instead of 2 minutes, for example, you would only have to wait until the next block, which is approximately 20 seconds. But so the question is this really doable on every blockchain? Can we really get to this value? And actually, it turns out for Cardano specifically, you can't. And I'm going to talk about why you can't. So remember how these pre-confirmation systems work. You say like, I will make the next block. Therefore, please buy my services. But how do people know you're actually making the next block? Right? Somebody says to you and says like, I will make the next block. Come buy my block space. How do you know this person actually is going to make the next block? Well, in certain blockchains, you can know for sure that somebody is making the next block. But in some other blockchains, you can't know for sure that somebody's making the next block. And so, in Cardano specifically, you can't 100% sure know who is making the next block. And the reason for that is because Cardano uses VRFs to basically decide who's making the next block. If you want to know more about like this VRFs and how they work, again, as I mentioned earlier, I have a video that talks about Cardano versus Algorand and their consensus, and how Cardano implements the Nakamoto consensus. And in that video, I go over the VRF, exactly how it works in details and how it compares to other systems. So if you want to know why Cardano has potentially, or sorry, if you want to know why Cardano can't know who's providing the next block at a mathematical level, that video will explain it for you. But I'll give you a bit of an answer in this video because it's important for what we're talking about, which is Cardano chooses the next block producer basically through a lottery. So I, for example, have, let's just say like I have 10 ADA on the blockchain. And in total, there's 45 billion ADA in circulation. So my chance of creating a block is 10 ADA over 45 billion if I register a stake pool. So very, very low, but still not zero. So you can think of this as kind of like a lottery. I have a specific percent chance. So for example, if I have 1 billion ADA, my chance would be 1 in 45 to make a block. So the more ADA you have, the higher your chance of making a block in the network. So you're essentially running this kind of lottery where depending on the ADA they have, the higher they have chances of making a block. But how do you share the results of this lottery? How do you coordinate this lottery? Remember, Cardano has maybe like 3,000 stake pools, right? So ideally, what you're not doing is having every single stake pool run some kind of votes, or not vote, a random like roll of the dice. So they roll a 45-sided dice, and then they have to share their dice results with everybody else. Because if you did this, then you have 3,000 stake pools all now sharing their dice roll information with everybody else, and the communication overhead is just way too big, right? This doesn't scale. So you cannot have everybody send information to everybody else about about the result of their dice roll. So in a blockchain like Algorand, basically what you do is you have a small set of people. So you can see in the video more information about this, but they choose like a small committee of people. It could be like 0 to 70 people. So instead of having all 3,000 stake pools, first you choose 70 nodes, like 0 to 70 nodes, and then the coordinate between them, which is now like a much more reasonable number. And the idea is that the exact people will change every single block. So it's not like it's the same 70 people all the time. Every single block, you have like another election of like, okay, who is going to be the small set that, coordinates between them. So this is a bit of like a very, very oversimplistic overview of algorithms, but you can, again, watch the video for more information. But Cardano, because we're not using BFT, we're using non-computable consensus, we don't want to require these kinds of committees of picking 70 people or whatever. Instead, we say, okay, well, people will just not talk to each other at all. There's just no coordination at all. Nobody ever talks to each other. Instead, the only way you quote-unquote talk is by actually making your block. So you making a block is basically you revealing you won the lottery. So it's like, oh, I won the lottery. I'm not going to tell anybody I won the lottery. I don't need to tell anybody I won the lottery. All I need to do is just make the block. And the fact that I make the block essentially reveals the fact that, I got lucky that a specific slot and that I get to make a block. But because there's no coordination ahead of time, nobody's talking to each other, you could have a situation where I roll a dice and I get, one. Like maybe if I roll a 45-sided dice, I roll and I get a 1. So I'm like, oh man, I got lucky, I got a 1. But somebody else rolls a dice and they also get a 1. Maybe like somebody got like a 2, somebody rolled a 7, somebody rolled a 13. I rolled a 1, but maybe somebody else rolled a 1 as well. So there could be multiple people that just by coincidence roll a 1 on their dice. And so we're both making blocks. So you might hear terms in Cardano like slot battles or block battles, which are essentially referring to this concept that it's possible for 2 people, or sometimes even like 3 or 4 people or even more, to be elected to create a block for the same slot. Of course, it's very unlikely to get, many, many people. The more people you have, the more unlikely it is, because it would require everybody to have rolled a 1, which is like very unlikely. So usually it's 1 person. Sometimes you have 2 people. Sometimes you have 3. But usually it does not really get larger than that. But the key thing is that because there's no communication, nobody's talking to each other, you don't know who's going to make a block ahead of time. And even if somebody advertises, I will make a block, in 1 day, I will make a block at this specific time, you cannot for sure know they'll actually make that block, because it could be that there's somebody else who is going to make a block at the same time, and maybe their block won and your block got rejected. So because you can't know 100% for sure that you will be making a block at a specific time, it becomes very hard to implement, or not preconditions, preconfirmations. Because remember, the idea of preconfirmations was that I can advertise ahead of time and sell my space, and so I'm selling space inside my block. But if I can't know I'm making the block ahead of time, how can I sell anything, right? So there's no guarantee of it, and so you have to fall back to stuff like Ouroboros Peras instead of having the faster finality you would get from these pre-confirmations. Now, one thing you might be tempted to do is say, well, okay, well, actually, we could solve this problem. We could have a new round where people talk to each other and share the fact that they're going to create a block, and then decide who makes the block, and then publish, right? So you add an extra round of information sharing, such that now we know 100% for sure this person will make a block, therefore allows for stuff like pre-confirmations to be created. The problem with this is that by revealing the fact that you're going to make a block ahead of time, you expose yourself to a DOS attack. DOS standing for denial of service. So if I know that you will make a block ahead of time, and it's for sure going to be you, and I know, where your node lives. Like maybe I know it's running on Amazon, or maybe I know it's running on Google Cloud, or I know it's running on Microsoft Azure, or maybe I know your address where you live, and I know your specific IP address for you running your node. If you're running like a node at home, I can use that information to try and attack your computer and stop it from producing a node. And this is called like a denial of service attack, and this can hurt the reliability of the network. So it could be that, ideally we would have had a bunch of blocks in the blockchain, because we know who's going to make the block next. Like maybe I'm able to successfully attack this person, and I'm able to successfully attack this person, and maybe I can't attack this person, I fail, but like maybe I'm able to attack this person. So you can see that by having the information of who's going to create a block next, it gives attackers who want to attack the network the ability to have a very targeted system where they go after very specific people and have a much higher chance of deteriorating the network versus, if there's no communication at all and creating the block is like your communication, by the time they create the block, it's too late to attack them. They've already created the block. They've already shared with other people. It's too late to attack them. So the fact that you're not sharing the information ahead of time, in this specific case, allows you to actually have a much more reliable network and much higher throughput. And so, for example, like Solana, which is a BFT style blockchain, uses the fact that you can know who creates the block next for performance benefits. Because if you know exactly who's going to make the block the next time, you know exactly which node you should connect to, who you should ask for information. It allows you to create a much faster network. The problem is, of course, Solana also gets attacked in this way a few times. So there's been cases where, because people know the next block that gets created by who, people attack that person and then deteriorate the state of the Solana blockchain, which can cause issues. And so there's trade-offs in all of this, right? So you could, with an approach like Solana, you can get faster block times because you know exactly where the next block will come from. And you can also enable stuff like preconfirmations that can give you even faster systems. So for example, like Ethereum supports this. So in Ethereum, you can find like these MEV operators that support these kind of preconfirmation systems. And they're used nowadays often for based rollups, which are rollups that submit transactions directly to layer 1 instead of having their own sequencers. So for example, like Paima Engine is one of the biggest base rollups. There's some other ones like Taiko as well. So different networks have decided to go with this approach to get the trade-offs. Then other networks like Cardano have decided to take the no information approach instead. So if you have a thought on which design is better, feel free to make your opinion known publicly, because I'll see the blockchain is owned by the people. So if people like a different set of trade-offs, obviously the blockchain can always be changed to reflect this. But note that knowing the who's going to make a block ahead of time does have a lot of trade-offs. It introduces these denial service attacks, but also more generally, it introduces a lot of potential MEV that you didn't want. So for example, you can see in Ethereum, a lot of people use MEVs for sandwich attacks. For example, like if you have a DEX and Bob is going to buy a token on the DEX, me as a stake pool operator, I can see that Bob is going to buy a token on the DEX. They've sent this transaction to me, and I'll sell the ability to front run you to the highest bidder. So MEV has a lot of different use cases, but this concept of sandwich attacks is the one it's most well known for, and for negative reasons, because oftentimes it leads to the person making the swap on the DEX to actually get a worse trade, because the fact they were going to trade was solely on open market, and then somebody leveraged the fact that they were going to place a trade to financially take advantage of them. So this MEV has some benefits, it has some improvements, but also has some downsides as well. So there's no free lunch on this. So that kind of concludes this video. Hopefully it can give you a good idea of the different ways we can try and speed up performance, and the different trade-offs, different approaches, and what has been done. One that I didn't talk maybe as much about as I should have, maybe I can add like a quick note at the end, is layer 2s themselves and partner chains and partner chains / side chains and Hydra give you also like a different flavor of speeding up block times. So if for example, like Arbitrum is one of the largest layer 2s on Ethereum. and they have 250 millisecond block times. Sorry. So on Arbitrum, they have 250 millisecond block times, which is obviously much faster than Ethereum, and they have kind of instant finality. And the reason they do this is because they're a layer 2 with their own sequencer set. So you don't fully inherit the decentralization of the Ethereum layer 1 because you're now running on a layer 2 that's operated by a single sequencer. In some of these other systems, like Hydra, you might have a set of a few different people running Hydra heads. On partner chains / side chains, you might have different consensus algorithms. So they have different network topologies, different network behaviors, but they can get you faster block times. And the concept of layer 2 is how do we basically provide these faster block times, better finality, while trying to inherit as much as possible the safety of layer 1. So this video is mostly talking about faster finality from a layer 1 perspective, but layer 2s are a very rich area of research for this kind of topic, and the fact that they provide such a better experience as far as block times and finality while trying to inherit safety from layer 1 is why layer 2s have been such a popular concept for the past few years. So I just wanted to give a side note on this, that if you're interested in solving this from other ways, there's other areas of research that are not layer 1 improvements, rather layer 2 improvements that are possible. And so I'd leave this as like a future research for you if you're interested in figuring it out. Hopefully you enjoyed this video. If you have thoughts about all this, which design decision you thought was best, let me know, especially because for Cardano specifically, if you're a DREP or you've delegated to a DREP, Ouroboros Peras will come live at some point, and it'll be up to the DREP to choose the protocol parameters of where do we choose the finality availability trade-off. So I look forward to that discussion. Thank you for your time.